lead metal. Okay, so suppose we have this lead metal. Okay, so what happens when we measure its resistivity versus temperature? Okay, at certain temperature this resistivity goes to zero. Okay, this resistivity suddenly drops to zero, and this transition temperature is called TC, critical temperature. Okay, so TC is what? TC is your critical temperature. Okay, so there are some material whose resistivity, okay, suddenly drops to zero, okay, below a critical temperature TC. Okay, this is the characteristics of superconductor. Okay, for some it may be, for example, for this lead, okay, it was 4 Kelvin. Okay, so different material have different TC. Okay, some may have 20 Kelvin, 30 Kelvin, and recently the material which were developed, okay, they have TC above 150K also. Okay, so the research is going on to bring more and more TC, so that we can use superconductor at room temperatures. Okay, this is the thing. So that's the one property of superconductor, that resistivity is zero. Okay, resistivity is zero below TC. Okay, so when T is less than TC, okay, your resistivity is zero. That is one property. The other property of superconductor is it is a perfectly diamagnetic. Okay, so for example, if I have a metal, okay, for a normal conductor, okay, so when I apply magnetic field, okay, so magnetic field lines penetrate inside this solid. Okay, so if I write the B, magnetic induction, so magnetic induction is given by mu 0. What is the magnetic induction? Okay, mu 0 H plus M. Okay, so inside the material the B is given. If it is a vacuum, you know B is mu 0 H. Okay, if it is the inside the material, okay, so inside the material B is given. Inside the material B is given like this, inside material. Now, so this is a normal conductor. Okay, normal conductor. Okay, so now what happens? So this is when T is greater than TC. Now when you cool this material, okay, what will happen? When you cool this material, what will happen? This all the magnetic flux line which were penetrating inside, okay, that there those magnetic field lines will get expelled. Those magnetic field line get expelled. Okay, so inside B is zero. Okay, at below when T is less than TC, okay, there is a no magnetic field inside a superconductor. Okay, if it shows this kind of property, then it is called superconductor. Okay, so I told you superconductor has two properties. One, when T is equal to less than TC, its resistivity is zero. Okay, so resistivity is zero, and at T is equal to TCC, all the magnetic field lines get expelled. Okay, that is called Meissner effect. That is called Meissner effect. Okay, Meissner effect. That means now if I want to characterize supercapacitor, this superconductor, so I can write that first thing, rho should be 0, T less than TC. Okay, and then second kya hai? If I write B is equal to 0 here, if I write B is equal to 0 here, so what I can write mu 0 H plus M. Okay, now I know the magnetic susceptibility is defined as M by H. Okay, M by H. So from here I can get what? M by H is equal to what? So I can write here mu 0. Okay, if I take H common, okay, this will give me 1 plus X. Okay, now if it is 0, so 1 plus X, so X is equal to minus 1. Okay, so X is equal to minus 1. So when magnetic susceptibility is equal to minus 1, then it is called perfect diamagnetic, perfect diamagnet, perfect diamagnetism, diamagnetism. Okay, so superconductivity means rho 0 and chi equals to -1 magnetic susceptibility. That is called perfect diamagnetism. ये पॉइंट क्लियर है दोनों? इट इज 2 पॉइंट्स आर क्लियर.
क्रिटिकल टेम्परेचर को क्या होता है, मतलब वो कंडक्टर जैसे बिहेव होता है या सेमी बिलो तो इसके, लेकिन एट क्रिटिकल टेम्परेचर क्या होता है?
क्रिटिकल टेम्परेचर ट्रांजिशन टेम्परेचर है. ओके, जिस टेम्परेचर पे आपका रेजिस्टिविटी 0 हो जाएगा. अब एग्जैक्टली तुम कैसे बोलोगे इस तरह से? कोई पर्टिकुलर टेम्परेचर है जहां पे वो कनेक्टिविटी 0 मिल जाएगा. ओके, दैट मींस दैट इज कॉल्ड ट्रांजिशन टेम्परेचर. तो यहाँ पे आपको क्या हो गया, आपका नॉर्मल स्टेट से, ओके, नॉर्मल स्टेट से सुपर कंडक्टिंग स्टेट. ओके, सुपर कंडक्टिंग स्टेट या स्टेट में आपका ट्रांजिशन हो गया. ओके, सो टीसी पे आपका रो इज इक्वल टू 0 हो गया. ओके, सिमिलरली टीसी व्हेन यू कूल T equal to TC. Okay, T equal to TC भी कर दो. Okay, if you are want to write more specifically, if you write T less than equal to TC, T equal to TC भी आ जाएगा, आपका मैग्नेटिक ट्रांजिशन होना शुरू हो जाएगा. फास्ट होगा, ट्रांजिशन डिपेंड करता है ना, बट ट्रांजिस्टर एकदम एग्जैक्ट एकदम परफेक्ट है, एक सडन है, और ट्रांजिशन स्लो स्लो है. so that you can call TC the transition temperature. और डिपेंड्स मटेरियल मटेरियल, किसमें क्या है, स्लो स्लो होगा TC के बाद, किसी में क्या हो जाएगा, एकदम 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 शार्प हो जाएगा. दैट विल डिस्कस नाउ. इज पॉइंट क्लियर?
Sir, can you explain graph once again?
Which one?
Graph, sir.
It is this graph.
No,
Or
no, no,
this
no.
one?
Transition. Yes, sir.
So what happened? Certain material, okay, when you cool them, okay, their resistivity suddenly drops to 0. Okay, so those kind of material are called your superconductor. Okay, so superconductor, your rho should be 0. At T less than TC, your resistivity should be 0, and T less than TC, the superconductor behave like a perfect diamagnet. Perfect diamagnetic means its chi value is -1. That means it will expel all the flux line through it. Okay, initially if temperature is more than TC, the magnetic flux lines are passing. Okay, magnetic field is magnetizing the material. You see, whenever you keep a material in magnetic field, either it will, the material can be a normal conductor, it may be ferromagnetic, it can be diamagnetic. Okay, so it's behaving like a normal way. Okay, so suppose in particular superconductor, okay, so these lines are passing through the this solid. Okay, inside they are penetrating. So once you are or that means you can say magnetic field is magnetizing. Okay, so once you cool them, these become perfect diamagnetic. That means all the line from this that get expelled. Okay, that means inside now B is 0. Okay, clear?
Okay, sir.
सर
Okay.
V इज इक्वल टू म्यू नॉट H प्लस M के नीचे जो स्टेप लिए ना, उसमें मतलब क्या सब्स्टिट्यूशन किया मैं थर्ड स्टेप में?
ये वाला में ना,
हाँ, क्या सब्स्टिट्यूशन?
M by H को मैंने काई लिखा है, M by H को मैंने काई लिखा है.
ओके ओके, क्लियर सर.
So this is your superconductor. Okay, two properties. Okay, now superconductivity, when a material is superconductor, okay, we can destroy superconductivity, okay, via magnetic field or via current और टेम्परेचर. ओके, तीन ही पैरामीटर है. अगर किसी सुपरकंडक्टर का टेम्परेचर बढ़ा दो TC, तो उसकी सुपरकंडक्टिविटी 0 हो जाएगी, वो नॉर्मल स्टेट में आ जाएगा. इसी तरह सिमिलरली इफ यू अप्लाई मैग्नेटिक फील्ड, ओके, beyond a particular value, that is called critical magnetic field. Okay, then critical magnetic field also can destroy your superconductivity. Critical magnetic field. Okay, magnetic field. Okay, so critical magnetic field का मतलब क्या है? The magnetic field required to destroy the superconductivity, okay, is called your critical magnetic field. And critical magnetic field is temperature dependent. So it is given by SC H naught 1 minus T by TC, okay, I think square, okay, square. So this is the equation for critical magnetic field at different temperatures. इसका मतलब क्या है? If your material is in superconducting state, okay, so your material is in superconducting state, okay, as superconducting SC, yes, superconducting state, superconducting, okay, say, and that is your normal state, okay. This is a normal state. So at t is equal to 0, you need, if you apply magnetic field, you need critical field equal to H naught, okay. And at t is equal to Tc, you need magnetic field equal to 0, okay. So if t is equal to Tc, if t is equal to Tc, then you require Sc equals to 0. If t is equal to 0 Kelvin, okay, 0 Kelvin, then what will happen? You require Sc equal to H naught, okay. So critical magnetic field क्या है? The magnetic field required to destroy or to make superconducting to normal transition is called your critical magnetic field, okay. So the minimum magnetic field require, okay, require to destroy superconducting state, okay, superconducting state, okay, is called your critical magnetic field. So T equal to TC पे तो अपने आप ही खत्म हो जाएगा, अपने आप ही सुपरकंडक्टिविटी डिस्ट्रॉय हो जाएगी, तो उसके लिए हमको मैग्नेटिक फील्ड की जरूरत ही नहीं है. So you can understand when you applying magnetic field, okay, the temperature of the sample is increasing. You can understand this way, okay. So because magnetic field will produce current in the sample, and current will heat the sample. So when current will heat the sample, automatically you are increasing temperature, okay. So या तो temperature बढ़ाओ या magnetic field बढ़ाओ. So if you are applying magnetic field and T is equal, and this is dependent on temperature, T is equal to 0 पे तो वैसे transition हो जाएगा, so you don't need any magnetic field, okay. T is equal to 0 पे you need Sc equal to H naught. This point is clear? Is this point clear?
Sir, when we increase the magnetic field, क्या होगा sir?
भी आप मैग्नेटिक फील्ड इंक्रीज करोगे तो क्या हो गया? मैग्नेटिक फील्ड इक्विवेलेंट टू करंट हो जाएगा ना. मैक्सवेल इक्वेशन से जानते ही हो. If you are increasing magnetic field, if you apply current in the sample, you create magnetic field. If you apply magnetic field, you are just equal to you are supplying current, okay. And when you are supplying current, that means you are increasing temperature, okay. This is not exactly है, पर ये है कि relation है, okay. So when you apply magnetic field, okay, at particular magnetic field value, okay, the transition will take place. It will go from superconducting state to normal state, okay. So this is the equation for TC. इसी पे question आता है exam में, okay. So I'm erasing this one. So this is the critical magnetic field, okay. Similarly, we can apply critical current, okay. Critical current or critical current density. Critical current or current density, or current density, okay. So suppose we have a superconducting ring, okay. We have a superconducting ring, okay. If T is less than Tc, और अगर इसमें मैं एक करंट फ्लो कर दूं I, okay, which is less than Ic, okay. So what will happen? This current, because in superconducting state there is zero resistivity, there is no resistance, इनफाइनाइट कंडक्टिविटी. सो क्या हो जाएगा? ये करंट क्या है? हमेशा इस लूप में फ्लो करता रहेगा, ओके. दैट इज कॉल्ड योर persistent current, okay. persistent current. So in a
current less than IC or greater than?
less than current less than IC, okay. Current is less than IC, okay. If I flow a current, okay, when your material is in superconducting state and I am applying very small current which cannot destroy is superconducting state, then what will happen? This current will keep on flowing in the loop. Okay, that is called your persistent current. Okay, now what is critical current? Okay, so critical current, okay, same like the minimum current required to destroy superconductivity. Okay, the minimum current require, okay, to destroy. Any question is there? आप पूछ सकते हो mic on करके, because it is difficult to see the chat box. Okay, so minimum current required to destroy superconducting state. Okay, superconducting state is called, okay, your critical current. Okay, and critical current is given by IC is equal to 2 pi R HC. Okay, whenever you flow a current, okay, in a wire, so it will create magnetic field, okay, which is equal to B equal to mu 0 I upon 2 pi R. Okay, and which is equal to H equal to I upon 2 pi R. So whenever you apply a critical current, it will produce critical field. Okay, and this current will destroy your superconductivity. Okay, similarly, if I want to calculate current density, so current density JC is what? IC by area. Okay, so IC means this 2 pi RC, 2 pi R HC, and I is pi R square. Okay, so pi by pi cancel, R cancel, so this will become 2 HC upon R. Okay, this is the formula for your current density. Okay, so whenever you apply critical current, it will destroy your superconductivity, that is IC. Okay, now I have 3 parameters. Okay, I have T, temperature, I have current density, and I have a magnetic field. Okay, so I have 3 parameters. Okay, so I have 3 parameters. By which I can destroy superconductivity. Number 1 is H, then we have a J, then we have a T, temperature. Okay, so when J equal to JC, in that time I don't require any temperature, I don't require any magnetic field, so I can destroy superconductivity. Similarly, if I am applying H equal to SC, that time I don't need any temperature, I don't need any current density. Okay, I can destroy superconductivity. Similarly, if I'm applying temperature, so when temperature T is equal to TC, okay, then I don't need any magnetic field, then I don't need any current density. Okay, so in this way I can make transition. Okay, so from one state to other state. Is this point clear? ये point clear है क्या?
Yes, sir.
Okay. Now सुपरकंडक्टिविटी दो चीजें, एक तो मैंने आपको बताया कि सुपरकंडक्टिविटी के अंदर एक तो आपका माइजनर इफेक्ट, हाँ
मत मिटाइएगा,
हाँ, एक तो आपका माइजनर इफेक्ट है और दूसरा आपका क्या है, दूसरा आपका इनफाइनाइट कंडक्टिविटी है. ओके, सो दिस वाज एक्सप्लेन, ओके, दिस थ्योरी वाज एक्सप्लेन by London equations. Okay, so London brothers was the first people, okay, who tried to explain superconductivity theoretically. Okay, so especially these two effects, okay, in metals, especially in metals. Okay, so put the heading now, London equations. Shall I rub this one now?
sir.
So put the heading now, London equations. The London equation. So London equation से हम क्या एक्सप्लेन करेंगे? एक तो हमारा infinite conductivity and then Meissner effect. Meissner effect. Okay, Meissner effect. Okay, so this theory was first theory to explain. Okay, first theory to explain occurrence of superconductivity. Occurrence of superconductivity. Okay. So if your material is in superconducting state, then there is a zero resistivity, zero resistance. Then that means when you apply a electric field, it should accelerate continuously. Your electricity velocity should vary continuously. Okay, so if I apply the Newton equation of motion, okay, dvs upon dt, I can write minus E upon E. Okay, so equation of motion. So this is the equation of motion. Okay, where Vs is what? Vs is, okay, velocity of electron in superconducting state. Okay, superconducting state. Now I know that the current density Js can be written as minus NeVs. Okay, so what is Ns? Okay, Ns is the density of electron. Okay, okay, density of superconducting electron. Okay, density of superconducting electrons. Okay, and Jc is the current density. Now superconductivity इन जनरली हम बोलते हैं सुपरकंडक्टर में दो तरह के इलेक्ट्रॉन होते हैं, एक तो होते हैं नॉर्मल इलेक्ट्रॉन होते हैं, एक सुपरकंडक्टिंग इलेक्ट्रॉन होते हैं. ओके, सुपरकंडक्टिंग इलेक्ट्रॉन क्या होते हैं? बिलो टीसी जो इलेक्ट्रॉन होते हैं सुपरकंडक्टर में, दे लाइक अ फ्लूइड, दे फॉर्म पेयर, दे आर इन द फॉर्म कूपर पेयर्स. ओके, दो तरह के इलेक्ट्रॉन होते हैं, एक तो होते हैं नॉर्मल इलेक्ट्रॉन्स जो टीसी पे होते हैं, और एक होते हैं इलेक्ट्रॉन जो पेयर्स की फॉर्म में होते हैं. व्हेन यू अप्लाई टेम्परेचर, ये पेयर क्या है, इन पेयर की जो एनर्जी, इफ यू अप्लाई एनर्जी, okay, that pair will broken and they will again become normal electrons. Okay, so your superconducting is, okay, this is the density of super. अभी यहाँ पे तो उसने तो नॉर्मल इलेक्ट्रॉन, उसने तो ये बोला कि this is the density electron in superconducting state. Okay, density of electrons, okay, in superconducting स्टेट. ओके, क्योंकि इससे जब इसने एक्सप्लेन किया तब तो बीसीएस थ्योरी आई नहीं थी, कूपर पेयर का कांसेप्ट आया नहीं था. सो यू अज्यूम द नंबर, दिस इज द डेंसिटी ऑफ इलेक्ट्रॉन्स इन सुपरकंडक्टिंग स्टेट्स. ओके, नाउ व्हाट आई कैन राइट इफ आई वांट टू राइट चेंज इन कंडक्टेंस. हाँ बोलिए
सर. कंडक्टर के इनसाइड तो इलेक्ट्रिक फील्ड जीरो होता है, तो
इलेक्ट्रिक फील्ड का जीरो कंडक्टर के अंदर. हाँ,
तो सर कैसे, मतलब पेनिट्रेट कैसे हो रहा है?
तो पेनिट्रेशन से इलेक्ट्रिक फील्ड का, मेटल का क्या मतलब होता है? मैग्नेटिक फील्ड है ना वो तो.
नहीं, कंडक्टर के मतलब आइडियल कंडक्टर के अंदर तो इलेक्ट्रिक फील्ड भी जीरो होता है.
हाँ, तो
सर कैसे, मतलब अंदर का जो इलेक्ट्रॉन है तो
हाँ,
कैसे
वो स्क्रीन करता है ना, स्क्रीन करता है ना भाई. आप किसी भी मेटल के ऊपर इलेक्ट्रिक फील्ड लगाओगे तो वो मेटल क्या पोलराइज हो जाएगा. पोलराइज होके जिस जो पोलराइज हो जाएगा मतलब क्या है, सरफेस पोलराइज हो जाएगा, और वो अपना एक इलेक्ट्रिक फील्ड प्रोड्यूस करेगा जो बाहर के
हाँ,
इलेक्ट्रिक फील्ड को कैंसिल कर दे. हाँ
फाइनल तो इनसाइड पे जीरो हो जाएगा.
हाँ हाँ
पहले तो पोलराइज करेगा, बट कुछ समय बाद तो इनसाइड में सब जीरो हो जाएगा, बाहर में
हाँ
इलेक्ट्रिक फील्ड.
हाँ.
तो कैसे सर ये, मतलब एक्सीलरेट कैसे कर रहे हैं इनसाइड का जो इलेक्ट्रॉन?
भी किसी भी मेटल में आप इलेक्ट्रिक फील्ड लगाते हो तो उसमें करंट फ्लो करता नहीं करता है. आप किसी भी मेटल पे वोल्टेज लगाओगे तो
हाँ
इन
हाँ
इन सरफेस, वो तो सरफेस तो मूव करेगा ना इलेक्ट्रॉन. तो
हाँ
इलेक्ट्रॉन तो मूव करेगा ही करेगा. ओके
अरे तो ये सब सरफेस पे हो रहा है।
जनरली
हाँ।
कंडक्टर भी तो इलेक्ट्रॉन सरफेस पे मूव करते हैं, हम ये मानते हैं सरफेस पे मूव कर रहा है। ओके सो दिस इज योर dgs अपॉन dt। ओके तो dgs अपॉन dt का हो जाएगा माइनस NSE dbs अपॉन dt। okay now you can put the value of dbs by dt from this equation, so I can write, okay so I can write here, this will become ne square, okay ns minus the e square, okay upon m ns e square upon m, okay and this will be your electric field dgs upon dt। okay now इस इक्वेशन से क्या पता चल
सर
रहा है,
माइनस साइन का आ गया, माइनस साइन आएगा ना?
माइनस से तो माइनस माइनस कैंसिल हो जाएगा, यहाँ पर भी तो माइनस है, एक माइनस वहां से माइनस से कैंसिल हो जाएगा जी। okay so this is known your first London equation। okay this is what this is called your this is first London equation। okay so ये इक्वेशन क्या बता रही है, if E is equal to 0, okay E is equal to 0 then dgs upon dt equals to constant। okay that means क्या constant तो इससे क्या पता चल रहा है हमको, okay and suppose if I'm increasing electric field, so this equation say a super current is freely accelerated by an applied field। a super current, this question says a super current is freely okay accelerated by an applied voltage, by an applied voltage। okay or this equation says, okay that in bulk superconductor, okay with no supercurrent, okay in a bulk superconductor, okay superconductor with no supercurrent, okay with no supercurrent or with a stationary supercurrent or with a stationary supercurrent with no supercurrent or with a stationary supercurrent, there is a no electric field, there is no effective electric field। ओके
मतलब करंट डेंसिटी कांस्टेंट हो जाएगी,
कांस्टेंट हो जाएगी विदाउट इलेक्ट्रिक फील्ड के भी। अगर आपने इलेक्ट्रिक लगा दिया फिर इलेक्ट्रिक हटा भी दिया तब भी उसके अंदर एक फिक्स करंट फ्लो हो सकता है। ओके दैट इज कॉल्ड सुपर करंट। वो करंट जीरो भी हो सकता है, ओके और कांस्टेंट भी हो सकता है। दैट इज कॉल्ड persistent करंट। दैट इज फर्स्ट, ओके योर लंडन इक्वेशन, फर्स्ट लंडन इक्वेशंस। ओके तो मतलब अगर persistent करंट फ्लो हो रहा है इसका मतलब क्या है, इनफाइनाइट कंडक्टिविटी, रेजिस्टेंस नहीं तभी तो फ्लो हो रहा है। okay so we are trying to explain two things. One is penetration, okay penetration of magnetic field, and we are why there is no penetration of magnetic field in the superconducting state, and why the conductivity is infinite. okay so conductivity infinite we can explain by this expression. So even though there is a E0, okay you are this we can have some current, we can have some current density in your material. okay that's the first London equation. Now shall I erase this one?
सर वो नीचे लाइन क्या लिखा है?
Stationary supercurrent, there is no effective electric field, there is no effective with no electric field. okay so now suppose if I take the curl of these equations, okay if I take the curl of this equation, del cross dgs upon dt, okay, and s e square upon del cross e, okay. Now I can write this equation as d upon dt, okay, del cross gs, okay, equal to n s e square upon del cross e, okay. Now I can apply del cross e. I know the Maxwell equation. From Maxwell equation, I know del cross e. Del cross e is equal to minus del b upon del t. Okay. So now if you write again this equation, so this equation I can write now d by dt, okay, del cross js, okay, minus n ns e square upon m del b upon del t. Okay, we can write this equation like this, del b upon dt. Okay, now, okay, what should I do now? If I integrate this equation, okay, if I integrate this equation, integrating this equation, integrating this equation, if I integrate this equation, this will give me what? Del cross js, okay, del cross js, and this will give me minus ns e square b upon m, okay, and some constant, okay. Now what London did, okay, London, he took c is equal to 0 arbitrarily, okay, he took c is equal to 0, okay, arbitrarily, okay, okay. So when it takes c is equal to 0, okay, I can write this equation, okay, delta js, okay, minus ns e square b upon m, okay. This is my equation, okay. This is called second London equation. I think this is second London equation. This is called second London equation. Now how can we explain the Meissner effect using this equations, okay. So now we have to explain the Meissner effect, okay, and flux penetration. So put the heading now, Meissner effect, and flux penetration, So if I want to explain Meissner effect of flux penetration, I can use this equation, okay. So I know that from Ampere's law, B dot dl is what? क्या लिखते हैं B dot dl को?
mu 0
I enclosed.
B 0 I enclose. Very good. Okay, B dot to enclose. Okay, and if I apply Stokes theorem, okay, Stokes theorem is for surface to line integration, del cross B, okay, del cross B ds.
dot d
क्या लिखता हूँ इसको?
dot d
B dot dl, huh? B dot dl, okay. So I can write and B dot dl, okay. And I know the I enclose is equal to what? J dot ds. I enclose J dot ds, okay. So from these equations, okay, what I can write? So this is the B dot dl, okay. So B dot dl equal to mu enclose, okay, mu enclose, okay, mu enclose, and mu is your I, you have j dot ds. Okay, so we can write from these equations. I can write my del cross b is equal to mu 0 js. Now, if I take curl of this equation, del cross b, okay, this will give me mu 0 del cross js. And if you open this one, तो क्या देगा? This equation
माइनस कर दिया गया
del dot b, okay, minus del square b, okay, and mu 0 del cross js, and we know the del b is 0, del dot b Maxwell equation is 0. So this will give me what? Minus del square b mu 0 del cross js. Okay, and I can write now a del cross. We have the value already. We know del cross js from second London equation. So from second London equation, I can write my del square b. Okay, del square b is equal to mu 0 and e square upon m. Okay, b. Okay, and I can also write this equation as 1 upon lambda L square b. Okay, where your lambda is what? 1 by lambda L square is equal to mu 0 n e square upon m. Mu 0 n e square upon m. Okay, so here lambda L has dimension of length. Okay, lambda has a dimension of length. Okay, and it is known as a London penetration length, and known as London penetration length. Okay, London penetration length. Okay, now shall I erase this one? Okay, so if
Yes.
if I take, so this is this equation. Okay, so this equation suggests, okay, this equation suggests there is a no constant field inside your material until b is not equal to 0. If b is equal to 0, then this constant. But other than b, there cannot be any other value, okay, inside your superconductor. That means superconductor can b cannot be constant, okay, other than 0. How? So suppose if I write a one-dimensional equation of the same equation, okay, if I write this is we have del square b, okay, 1 upon lambda L square b. Okay, so if I write one-dimensional equation, del b upon del x square. Okay, so this can be, I can write 1 upon lambda L square b. Now the solution of these equations, okay, the solution of these equations are given as b 0 e minus x upon lambda L. Okay, this is the solution of this equation.
Sir, what is that? B of x?
B naught bx equal to bx equal to b naught e power minus x upon lambda L.
Okay, sir.
Okay, so this is the solution of this equation. Okay, so now what I can write that
सर
हाँ बता
आपने
रहा
लंडन पेनिट्रेशन डेप्थ के बाद क्या बताया सर
किसमें
एक लाइन बता
किसमें
सर पेनिट्रेशन डेप्थ के बाद आपने क्या बताया
ये भी पेनिट्रेशन डेप्थ है, ठीक है। तो पेनिट्रेशन ये इक्वेशन हमको क्या सजेस्ट कर रहा है कि आपका जो बी है वो मटेरियल के अंदर कांस्टेंट नहीं हो सकता है। अगर बी कल 0 है तो 0 रह सकता है, अदर देन बी 0 देयर कैन नॉट बी एनी अदर वैल्यू। ओके, तो अभी इसको एक्सप्लेन कर रहे हैं अभी। तो इनसाइड मटेरियल your b cannot be constant other than 0. 0 it can be 0 everywhere, but other than value it cannot be constant value inside solid. Okay, so now you have this your solid मतलब यहाँ पे सुपर कनेक्टर की बात कर रहे हैं, इनसाइड सुपर कनेक्टर। So we have
ब्रैड स्क्वायर टर्म के वजह से
hmm
ब्रैड स्क्वायर टर्म के वजह से वो कांस्टेंट नहीं होगा
इसकी टर्म पे भी ये इसकी टर्म से ना एक्सपोनेंशियल डिक्रीज कर रहा है ना. ओके, सो if I draw this one, if I draw this curve, okay, so I have a b versus distance inside superconductor. Okay, this is falling like this. Okay, this falling like the distance. So this is x direction distance. Now if okay, if I take x is equal to lambda l, okay, your b will be what? B will be b naught by e. Okay, so is x equal to 0, you have b naught. X equal to 0, you have b naught, and as you increase the distance, okay, so when your x is equal to lambda l, okay, your b is equal to b naught by e. Okay, from here also you can define the London penetration depth. Okay, so what is the London penetration depth? Okay, the London penetration depth is distance. Okay, the London penetration distance or depth is the distance, okay, at which it's the distance at which at which the London penetration depth is the distance at which the magnetic field okay drops to 1 by e of times of its 1 by e times of its value at surface, its value at surface. Okay, तो surface पे जितनी वैल्यू है उसका 1 by t टाइम्स जब डिक्रीज होगा, दैट इज डिस्टेंस कॉल्ड पेनिट्रेशन डेप्थ. अब इससे हमको पता क्या चल रहा है. ओके, तो सबसे पहले तो हमको फॉर्मूला लिखना है लैम्बडा एल हमारा क्या है, पेनिट्रेशन डेप्थ हमारा क्या है. तो ये बता रहा है कि अगर पेनिट्रेशन डेप्थ इनफाइनाइट है, ओके, पेनिट्रेशन डेप्थ इनफाइनाइट है तो आपको बी 0 हो जाएगा. इनफाइनाइट का मतलब है अगर पेनिट्रेशन थ्रू आउट द मटेरियल हो गया तो बी 0 होना चाहिए. तो पेनिट्रेशन थ्रू आउट द मटेरियल, इनफाइनाइट का मतलब यहाँ पे क्या है, इफ सरफेस मटेरियल थ्रू आउट द लेंथ अगर पेनिट्रेशन हो गया then your b should be 0. यही तो माइजनर इफेक्ट होता है. so is we can understand this in this way. if you have a lambda l, so lambda l क्या है, lambda l is under root, okay, under root m mu 0 ns e square. Okay, this is your formula for penetration depth. Okay, now you can see here your penetration depth L, okay, is inversely proportional to your under root of ns. Okay, ns is what, super electron current density or density of electrons. Now what will happen if you increase the temperature? Okay, if you increase the temperature, what will happen, this ns will decrease. Okay, so if you increase the temperature, what I can write, if t goes high, your ns, okay, your ns will go down. if t goes high, your ns will go down. Okay, and if t equal to tc, your ns is equal to 0. so when ns is equal to 0, your lambda s is what, lambda s is infinite. Okay, so penetration is throughout the region, throughout the solid dimension, and once lambda s is infinite, your b is 0. Okay, b is 0, that is your Meissner effect. Meissner,
सर एक बार ns बताओगे क्या है?
ns क्या है, सुपर इलेक्ट्रॉन करंट डेंसिटी. ओके, सुपर इलेक्ट्रॉन करंट डेंसिटी.
टेम्परेचर बढ़ेगा तो नंबर ऑफ एटम्स भी बढ़ेंगे ना.
सो अगर इफ टेम्परेचर बढ़ रहा है तो आपका जो इलेक्ट्रॉन्स है, सुपर इलेक्ट्रॉन है, दैट विल कन्वर्ट इन नॉर्मल इलेक्ट्रॉन्स. समझ में आ रहा है? ओके, In superconductor, we have two types of electron: normal electrons and superconductor electron. So when you heat this, the density of superconducting electron will decrease. Okay, and this becomes zero. T equal to TC पे पूरा normal हो जाएगा. Then your normal electron density. Okay, then this becomes zero. Okay, and when this becomes zero, your lambda has become infinite. That means lambda become infinite. That means your B is zero. That is perfect diamagnetism. Perfect डाया थ्योरी है, उसकी इक्वेशंस को इसी तरह समझने की कोशिश करते हैं. Okay, this is perfect diamagnetism. Now here, from here, this lambda. Okay, lambda also is temperature dependent. Your penetration depth is also temperature dependent. तो किस टेम्परेचर पे कितना पेनिट्रेशन होगा, that also, so we can write lambda LT, that is given as lambda 0. Okay, 1 minus T upon TC का स्क्वायर पावर 4, सॉरी 4. इंपॉर्टेंट रिलेशन याद रखना, पावर माइनस हाफ. ओके, सो दिस इज द वेरिएशन ऑफ योर penetration depth with temperature. Okay, now let us solve a few problems. Okay, एग्जाम में जब भी हमको प्रॉब्लम्स ही करनी है मेनली.
एक्सक्यूज मी सर.
हाँ बोलिए.
सर जब हमारा लैम्डा एल इंफिनिटी पे चला जाता है तो उस टाइम तो हमारा जो मैग्नेटिक फील्ड है वो पूरा पेनिट्रेट कर जाएगा ना मटेरियल में,
जीरो हो
तो
जाता है,
नॉर्मल स्टेट में आ जाएगा.
मैग्नेटिक फील्ड
सर
जीरो हो
ये
जाता है. हाँ, अच्छा उल्टा बोला क्या मैंने?
हाँ,
हाँ,
माइनस
सॉरी. हाँ, टी को टीसी पे वो मैग्नेटिक फील्ड पूरा पेनिट्रेट कर जाता है. करेक्ट, पूरा पेनिट्रेट कर जाएगा, मतलब नॉर्मल स्टेट में आ जाएगा. मैं उल्टा बोला था. लैम्बडा इज इनफाइनाइट, मतलब आपका बी पूरा पेनिट्रेट कर जाएगा.
वो नॉर्मल स्टेट में आ जाएगा.
हाँ, नॉर्मल स्टेट में आ जाएगा. ओके,
लैम्डा मिनिमम होगा तभी वो सुपर कंडक्टिंग स्टेट.
यस, तभी सुपर स्टेट हो. So just give me 1 minute. The problems देख रहा हूँ. Where did I check the problems? So mainly problems जो आती हैं. Okay, so I'm writing one question. Okay, so a superconductor tin has a critical temperature of 3.7 Kelvin. Okay, a superconducting, we have tin. Okay, in superconducting state, conducting state, tin, okay, has a critical temperature Tc is 3.7 Kelvin. Okay, in zero magnetic field, in zero magnetic field. Okay. So when you don't have a magnetic field, your Tc is equal to 3.1 Kelvin. Okay, and a critical field दे रखा है SC, and critical field SC of 0.0306 Tesla. Okay, at 0 Kelvin. Okay, so बोल रहा है find the critical field. Find the critical field. Okay, at 2 Kelvin. तो आपको क्रिटिकल फील्ड दे रखा है 0 केल्विन पे दे रखा है. 0 केल्विन पे जो क्रिटिकल फील्ड होता है दैट इज इक्वल टू व्हाट? H नॉट. So we know the equation of critical field. This is H naught 1 minus T upon TC का स्क्वायर. ये तो इक्वेशन है.
Yes.
So T is equal to 0 केल्विन पे आपको H नॉट दे रखा है. H नॉट is given and TC also given. So at T is equal to 2 Kelvin, you need to calculate the SC. बताओ कितना आ रहा है?
Sir, TC how much? 3.7.
3.7 Kelvin.
Okay, sir.
Sir, 0.021 Tesla.
Yes, so it will come 0.02166 Tesla. Okay. Now similarly, there's one more question on critical current. Okay. So the question is, calculate the critical current which can flow through a long thin superconducting wire of aluminum of diameter 1 mm. Okay, so diameter of wire is given 1 mm. Okay, the critical magnetic for this is aluminum wire. Okay, the critical magnetic field for aluminum is critical magnetic field SC. SC is given as 7.9 into 10 raised to power 13 ampere per meter. SC value is given. Okay, so he's asking calculate the critical current IC. कैसे निकालेंगे? What is the formula for critical current?
7.9 into 10 raised to 30 or 3?
क्या?
7.9.
3.
Sir, 2HC by R ना IC.
तो IC का फॉर्मूला क्या है?
Sorry, 2 pi R HC.
2 pi R SC. Yes, 2 pi R SC. इतने फॉर्मूला है. IC निकालो. Diameter is given 1 mm. Okay. So 1 mm को कर लो मीटर में कन्वर्ट. डायमीटर देखा तुमको रेडियस निकालना है पहले तो. Okay. So diameter is 1 mm. Okay, -3. So R क्या हो जाएगा? R हो जाएगा 0.5.
0.5 into
10 to the power -3. Okay, or 5 into 10 to the power -4. So if you solve this one, 2 into 3.14 into 5 into 10 to the power -4, SC is 7.9 to 10 to the power 3. This should give you value 24.806 amperes. Okay, so I'm stopping here. Okay, we'll meet tomorrow again the same time. So I think it will take 3 classes to complete superconductivity. कल हम थ्योरी करा देंगे, परसों फिर एग्जाम की अभी प्रॉब्लम्स और थोड़ा बहुत थ्योरी जो बच्चे का वो कर देंगे. 3 क्लास लगेगा एटलीस्ट. So thank you very much. I'm stopping here. Thank you.
Thank you, sir.